Hey, my name is Yuri, and in this session I want to take you through how attackers will try to exploit API vulnerabilities, the risks that are associated with that, and what you can do about it. I'll be taking you through a live hacking demonstration where I show you real-life techniques that will be used against APIs, and I'll show you the effects and the outcomes of those attacks. But first, API security is a very hot topic today, and I want to share some information with you to illustrate why it is so important. This is a quote that I took from the report published by Gartner at the end of 2021 called Predicts 2022, APIs Demand Improved Security and Management. And one of the things that really stood out for me is that by 2023, which is today, Gartner predicts that API abuse will move from infrequent to the most frequent attack vector. This means that attackers are shifting their attacks from other areas of your attack surface, mainly web applications, file shares, and other things, to APIs as the most frequent attack vector. APIs have a number of characteristics that make them really interesting to target. They are designed for openness. They are designed to exchange information, access information, modify information in a secure way. But if you can work around the security controls and mechanisms, you have access to abundance of information. That results in data breaches for enterprises. And by 2025, more than 50%, more than half of data theft will be due to unsecured APIs. If we look at the cost of a data breach, and these are results from a survey done by IBM over the course of 2022, what they found is that the average cost of a data breach averaged $4.35 million in 2022. One breach would result in a cost of more than $4 million for the impacted organization. And in this survey, these are all companies that have experienced a data breach in 2022. 83 of those impacted organizations actually experienced more than one breach. They weren't just breached once, but multiple times. And breaches caused by the use of stolen or compromised credentials, gaining access to the system in an unrightful way, those types of breaches have the longest life cycle. It can take up to 327 days before the breaches are located, identified, isolated, and resolved. That's almost a full year. So in this demonstration, I want to show you how attackers will search for API vulnerabilities. I want to explain to you how attackers will go about try to identify what it is that you have in terms of capabilities in your APIs, what type of access to data that might provide them, if they can get the right permissions, and see if they can work around those permission controls or security controls and unrightfully gain access to information. I'll demonstrate some of the tactics that attackers will use to exploit those vulnerabilities. So the first is really about reconnaissance. The second topic is really about, if I know that a vulnerability exists, how will I try to exploit it? And thirdly, I will explain to you the measures that you can put in place to protect your APIs. So to be able to protect your APIs, one of the first things that you need to do is to think like a hacker. It takes one to know one. And you have to understand the process that a hacker or an attacker will go through when they attempt to access APIs, when they attempt to breach APIs and breach data. And essentially you can separate this up into 4 phases. The first phase is typically reconnaissance. This is where an attacker will try to identify what are the types of endpoints that you have. They'll, for example, do a scan of your domain name, trying to figure out what are all the domain names you have, what are the IP addresses, what types of ports do you have exposed, etc. Mapping out the infrastructure that you have. And then they'll try to reverse engineer. From that infrastructure, they will try to reverse engineer the APIs that you have. And reverse engineering could be something as simple as just using a web application and seeing what type of traffic that generates, and then reverse engineering that traffic into an API. This is actually the example that I'll be walking you through today. Thirdly, they'll go about scanning. Scanning can mean many things. For example, they could use tools to go and scan things like versions of operating systems, versions of web servers, see if you're using vulnerable versions of third-party libraries, etc., that they could potentially exploit. But scanning also means, trying to identify what types of attack plays might be successful. And then lastly, they'll go and execute attack plays. This is where they'll actively start to try and breach your API. So I want to take you through a demonstration. It's a demonstration that uses some real-life techniques, both on the application side as on the attack plays that we'll be executing. So I have an application. It's actually open sourced. You can find it on the website or on GitHub, sorry. It's called the Deliberately Vulnerable E-commerce API, and it's a demo application that has a Node.js-based backend, which is an API-first application that has deliberate vulnerabilities. And there's a view-based front-end web store that uses the API in the backend for all of the functionalities of the web store. And the attack plays have actually been documented and scripted. So you can go ahead, just visit the GitHub repo, and you'll find all the information there. During the demonstration, I'll be using a couple of tools. Some of it will be scripting that I've written myself. Other things will be open source tools that are available to anybody in the industry. Anybody can access those tools, use them, install them if they just spend the time to learn to use them. First will be Firefox with Foxy Proxy, because I'll be using a tool called Man-in-the-Middle Proxy, MITM Proxy. And Man-in-the-Middle Proxy is essentially a local proxy that you can install on your local machine as an attacker. You can proxy all the traffic from your web browser through Man-in-the-Middle Proxy, and Man-in-the-Middle Proxy has a number of very nifty features that help you understand what type of web traffic is being generated, what types of API calls are being done, what are the requests, what are the responses, etc. I'll be using Postman to try and reverse engineer some of the requests that the application is making and running some tests. And I'll be using two tools which are often used with attempts to crack secrets, passwords, signatures, etc. The first one is called Hashcat, and the second one is a Python-based tool which is called JWT tool. So these are all things that are out there in the wild. They're open source. These are tools that have been created for the purposes of penetration testing, etc. But obviously these are also being used by attackers out in the wild. So let's move to the demonstration. All right, so this is my deliberately vulnerable application. This is the e-commerce website where we have a shop. We can go and browse the shop, look at the product details, obviously add things to our shopping cart, and then go and order that. In the process of doing all of that, as a customer, I will be providing information, things like my personal information, address, phone number, email address, but also payment information. I'll be providing my credit card and other things to actually order the products, pay for them, and get them shipped to me. My home address will be there. So there's a lot of PII and payment data that is being captured in this application. And as an attacker, my goal, or as a penetration tester, my goal is to try and access that data. So what I've done here is I've set up Firefox and Firefox with Foxy Proxy. You could use any type of proxy plugin or proxy extension. You could even just set your network system settings to use the proxy that you want to use. In this case, I'm using Man-in-the-Middle Proxy, which I've set up on my local host. And you can see that output here to the right-hand side. So Man-in-the-Middle Proxy is essentially something that right now sits between my Firefox browser and the actual web host or API host in the backend. So all of the web traffic that I generate through Firefox will be redirected through Man-in-the-Middle Proxy and then forwarded on to the real destination. Man-in-the-Middle Proxy will log all the calls and give me the possibility to go and inspect those calls. Inspect requests with all of their parameters like headers, query parameters, payload itself, and also inspect all of the responses with all of their details. Normally, man-in-the-middle proxy would be giving us all the traffic generated by the browser. In this case, I wanted to limit it for clarity during the demonstration. So I've applied a filter that makes sure that we'll only see our API traffic. So we'll only see the API calls that are being made by this web application. So let's have a look. Let's start with refreshing the page and see what happens. So we see that one call is logged. We see a get operation performed against the product endpoint. And we have two query parameters, a page 1 and a size 10. Let's see, visit page 2. We see, okay, page 2, size 10. So we've got this down. We can visit one of the product details pages. And again, we see a product/ID. So in this case, we're visiting an individual product, common pattern with REST APIs, and we're getting the details back. Let's have a look at what man-in-the-middle proxy is actually collecting for us. So let's look at the first one. First one, request, we have two query parameters and a bunch of headers. Nothing here is too interesting for us at this point. I just want to showcase what man-in-the-middle proxy gives us. And it gives us the full details of everything in the HTTP response as well. For example, our web server is an Express application, so Node.js with Express. We see we're sending JSON back. We're getting a full set of JSON information back. This is actually 10 elements in the collection of products. Cool. So let's have a look at the details for an individual product. We see here the request goes to the endpoint product/12. So we're fetching the information for product number 12. And we see in our response that we get the details back for a single product. Interesting. So this is how the whole setup works. This is how man-in-the-middle proxy will help me perform some reconnaissance, understand what the APIs are and the endpoints are behind this application, what are the resources, what are the methods being used, and maybe I can reverse engineer something from here. So let's clean the flow and let's sign up. Right? If we want to test this application and figure out all the things that happen within the application, we should just sign up as a user, as a customer, and use the application as it was intended to be used. So let's say I'm attacker1@gmail.com. We'll put in a password, just check that I'm putting in the right one. Yeah, this is the one I'll be using for the whole session. My name is Attacker. And last name is 1. All right, let's sign up and see what happens. Okay, so I've signed up, and obviously for usability reasons, I've automatically been signed in as well, apparently. Remember, this is a demo application. I'm not trying to tell you how the application should be built. This is deliberately vulnerable, right? So let's have a look at the things that have happened in the backend. We see two post operations and then a get. We're familiar with the get operation, right? It's just redirected us to the home page. It's getting us all the products, page 1, size 10. But there's been two posts to an auth signup endpoint and an auth login endpoint. These are interesting, so let's go and have a look. The post to the auth signup endpoint had a payload, which seems to be the payload from the web form, right? It has my email address, first name, last name, and the password that I entered. I can see this information because the proxy is on the local end. So I can actually see the information. Even if we're using SSL traffic, man-in-the-middle proxy will have full access to what I'm sending as a client. So I see all the information here, and I see that my response is simply a 200 OK. There's no payload, it's just giving me an OK back. All right, interesting. And then on the post side for the login, we see that, again, the client, the web application is passing in the email and the password. And in our response, we're getting a token back. All right, so this application is using tokens. There's a variety of different types of tokens that you could potentially use. And it's not that hard to identify which type of token is being used. But what we have here is a token, which is a JWT token, so a JSON web token. Interesting. So we've found these by working through how the application works, simply using it and looking at man-in-the-middle proxy. Now let's see if we can do some reverse engineering. And I'm going to use Postman. I've actually prepared a few things here. So I'm going to try and sign up with a random email and password. And then next I'll be logging in with that email and password. So let's do this first. I'm actually using a pre-request script which generates me the random email. And then in the login action, I'll be using the same parameters, email and password. In the tests, I'll be storing the token. So I'll be storing the token so I can reuse it in further attack plays. This is normal, standard Postman features. So I recommend you dig into Postman a little bit. Postman is free to use, so all of these capabilities are available to anybody who wants to. Right, so we're trying to achieve the same thing now, but from Postman. So I'll try and call my API host and sign up. All right, cool. I'm getting a 200 OK back. All right, so now I'm going to log in as this user. Send it. And I'm getting a token back. Interesting. So I've been able to reverse engineer this using Firefox, Foxy Proxy, man in the middle. Now I'm just building up a library essentially of information inside Postman. I'm documenting the things I found inside Postman so that I can go and use them afterwards. Now let's talk about a first type of attacks that this application could be vulnerable to. And the first type of attacks is token attacks. Okay, so the type of token attacks that we could use as a penetration tester or attacker will vary obviously depending on the types of tokens that are being used. Now it's pretty easy to identify the type of token that is being used, and in this case, I can tell you it's a JWT token, which is a very commonly used type. So with JWT tokens, you may expect this to be secret in the sense that the content seems cryptic, encrypted, but the reality is it isn't. This content is encoded, and this is just an example token, but if I paste the token that we receive back from our API, we see that there's a lot of information inside that token that is accessible to the client. So a JWT token is an encoded and signed token in this case. So what we see is that token is partitioned into 3 bits, 3 parts. First, we've got a section which indicates the header. Then there's a dot and a section that contains the payload of the token. And then the final section contains the signature. In the encoded values, we see this in the red, purple, and blue colors. And on the decoded side, we see the actual legible information as it has been decoded. So we see that the algorithm that was used is an HS256, which means that the token was generated and signed using a 256-bit secret key and a hash. We see the payload, which contains whatever was set by the application at the time of signing this token. And then we've got the verify signature bit where we can see if we put in the super secret key, should we know it, we'll be able to validate this token and its content. So the way that this works is the server generates this signed token with its content and that hashing algorithm and its super secret key. That super secret key is what enables the server in subsequent requests to validate the JWT token. When the token comes in, it can use its super secret key to validate that nobody has changed the contents of this token. For example, attackers might try to change the hashing algorithm, for example, to a non-algorithm, which exists. No hashing, nothing applied, just encoded. Or they might try to swap out the email address for another email address, or the ID for another ID value. They'll try and apply all of these techniques to see if they can somehow access another user's data. But in this case, because it's signed with a key, the server can validate that key and it will invalidate any token that has been tampered with. So in terms of vulnerabilities introduced by this token, there's a couple of things we need to look at. First, let's look at the payload. So the payload of this token has too much information in it, honestly, right? There's a couple of things we can derive here which make us, as an attacker, smarter about the backend application. We see this underscore ID field and the underscore V field. This tells us that the backend application is actually using MongoDB as a storage. This is a very common data format or data structure when the backend application uses MongoDB, which tells us that this is a MongoDB object ID, right? This is the unique identifier of that JSON document in the Mongo database. And we know that these IDs, at least with older versions of Mongo, give away some clues as to the time at which this object was generated. Now, that doesn't bother us here. We're not interested in that. But we're interested in some of the other details here. So we see this issued at timestamp. This tells us when the token was generated. But normally I would expect to see an expires at exp tag in this payload as well, which tells us that the token would be valid, for example, for 15 minutes, which is a best practice recommendation when you generate JWT tokens, to have them expire. If you don't have them expire and this token is compromised, attackers could potentially endlessly reuse this token without you having the possibility of revoking that token. The only way you could revoke that token is by revoking all tokens at the same time by changing your secret key with which you sign and verify signatures. So too much information for sure. The obvious flaw here is obviously that, the password, although hashed, so it's not in clear text, it's a hashed value, is inside this user object as well. So why am I telling you this is hashed? Because I can see that based on the format of this hash string, this $2b means that this value is a hash of the original password that was created using the bcrypt algorithm. The $10 tells me that a cost factor of 10 was applied when generating the hash. So essentially this means we're using bcrypt. We've done 10 rounds of hashing subsequently to generate this value. It is very hard to go back from this value to the clear text value. It's not impossible. With enough compute power, you can guess the right password, guess the right original clear text value, but it is really hard. Bcrypt is generally considered to be very safe because of its high cost factor when generating these hashes. But again, there's too much information here. This should never be sent to the client because the client now does have that hashed value of the password, and they could potentially spend any amount of money, throw any amount of hardware at it to try and crack this password. And they will be able to crack it, given the right mix of hardware and money you're willing to spend and time you're willing to spend to try and crack it. So this is definitely too much information. The other part of information we know is that this is obviously a JWT token. It was generated using a hashing algorithm with a 256-bit key. So an attacker could go and try and guess the secret key that was used to generate these tokens. This would be interesting because unlike guessing a user's password, if you can guess the secret key for the JWT token, you can actually generate your own tokens. For existing users, non-existing users, you don't even need to know what the server would typically put into the payload field. You would be able to generate your own tokens that would be accepted by the server side, if you can guess that. So obviously, because JWT tokens have a lot of good properties, they're commonly used for various benefits. They also have a couple of weaknesses that you need to take into account and be smart about. So best practice recommendations would be obviously sanitize the payload data because you don't want too much information here, but also make sure that you use long super secret keys to generate your JWT tokens. Now, when attackers and penetration testers know that you're using JWT tokens, there's a couple of things that they'll go and try, and I'll give you a few examples. So first I want to show you a tool called JWT_tool. This is an open source project. It's actually written in Python, which has a collection of scripts that you can use to try and break JWT tokens. So I'll use another token just to show you. This is a token for a user that in the web application has a complete profile. So I'll add my token value to an environment variable. I'll show you the token value. So this is very similar to what you've seen just moments ago. And then I want to use my JWT tool to inspect the token. So JWT tool, with just the argument of the token, will parse the token and show me something that is very similar to what JWT.io, the website, showed me. Right? We see that our payload is more complete here because our user profile is more complete. So we see that the application really is just dumping the whole user object into the payload without sanitizing it. We earlier mentioned the password, which is a potential vulnerability. It should never be in there, but still expensive to crack. But information like the credit card number is in here in clear text as well. So obviously we're dealing with a case of excessive data exposure, which is one of the OWASP API top 10 vulnerabilities. Now, in theory, this token is only available by the client that just logged in, right? So this is something that is secret and unique to that one login session for that one client. So the impact when this would be compromised is relatively small. But attackers will try to compromise these tokens at larger scale, for example, through cross-site scripting, or very commonly today, phishing attacks. Right? If they can get you to log into the backend using their own fake front end, they can start to harvest tokens that in this case contain a lot of information that they shouldn't have, and actually never expire. So they can, for eternity, impersonate you and place orders in your account, etc. So we should be really careful with the amount of information in JWT tokens, and this is one of the first vulnerabilities that we've highlighted, which is excessive data exposure. Now, as I mentioned, there's two other vulnerabilities here because the password is here, or potential vulnerabilities. Because the password is here, we can try to crack the password. Now, if we go and try to crack the password, we'll need to use a tool, I mentioned it earlier during the presentation, called Hashcat. And Hashcat is one of the options, but Hashcat is very commonly used to try and guess, essentially brute force or dictionary. I will explain that in a minute. Brute force the original value. So we're going to do a game of guessing, essentially. So let's have a look at Hashcat. Hashcat is another tool just like JWT tool. This is a more general purpose tool. Hashcat is an open source tool that is used a lot to try and break secrets. And it will try to break secrets in multiple different types of ways. The two most common ones are brute force and dictionary attacks. So with brute force, it'll actually try to go through all the combinations for a potential length of a password and try them all out one by one. In dictionary, you actually provided a list of possible passwords, and it'll go and try each of those possibilities one by one. So that's the difference between a brute force and a dictionary attack. Obviously, with dictionary attack, you're trying to be more specific, have a higher chance of success. But in the case of random passwords, usually the brute force attack is really what you need. But it's also the most expensive one to run. So let's have a look. I've prepared a few demo scripts here. In this directory, I can show you. I've got a stolen hash, which is the password, and I've got a stolen JWT token. Let's start with a stolen hash. So show you this. This is the value of the hashed password as it was stored in that JWT token payload. So to go and crack the hash, we need to use Hashcat and give it a couple of parameters. So I'll just show you what that script looked like. So crack the hash. You see I'm using Hashcat. I'm running it with the 3200 indicator for algorithm, which is bcrypt. I'm putting in the stolen hash as the value. I'm telling it to brute force against the password. I'm using only lowercase and uppercase characters. The maximum length is 12 characters. And I'm going to increment starting from 6 characters. I know that the password values for this application, because the registration form tells me, is a minimum of 6 alphanumeric characters and a maximum of 12 alphanumeric characters. So Hashcat will run through all of the possible combinations between 6 and 12 alphanumeric characters. So let's run the script and see what it tells us. Now, the first thing this tells me is that I don't have good hardware to do this. This shouldn't surprise you. Hashing is something that, for example, is also very common in blockchain and Bitcoin mining and that kind of thing. Hashing is a compute-intensive mathematical operation, which GPUs are really, really good at. So graphical processing units, GPUs, are actually more efficient at doing this than central processing units, CPUs. So by default, Hashcat takes the GPU in my machine, which is pretty weak because this is a Mac Mini. But hackers that really want to crack hashes will obviously use GPU hardware. So they'll use things like mining rigs or GPU instances on some cloud provider to run this at a much faster rate than I can on this machine. Let's have a look at the status for Hashcat right now. So this is telling me that we're doing bcrypt, so blowfish. This is our hash target. We started a minute ago, and the estimated time for finding the clear text value through brute forcing is roughly 9.5 years on my machine. So obviously, when I told you earlier that having the hashed value in the token payload is a security vulnerability, it is a case of, well, excessive data exposure or security misconfiguration, which of the two you could debate, but it definitely shouldn't be there. Now, if it is there, it is still very expensive to try and crack that one password for that one single user. So yes, it can be cracked. And if you're willing to spend money and time, you can crack this relatively quickly. But still, on general, something that is 8 characters would take you months to crack. So with a good password expiration policy, resetting the passwords every few weeks or months, etc., you should be able to minimize the risk here. So it's not just about having too much information in the token. There's more that comes into play here. But in theory, anybody willing to spend money and time will be able to crack this. We're not going to wait. So this was the password value in the token, but what about the token secret itself? Can I crack the JWT token? So again, we've got this stolen JWT. Let me just show you. There we go. So this is a JWT token that we've compromised somehow. In this case, I've just logged in as that user, obviously. But imagine that an attacker can compromise it. Can they crack this? So let's have a look at the crack script for JWT. This uses Hashcat again, but with an algorithm of 16,500, which is what we're doing here, which is HS256 for JWT. We've got this stolen JWT, and we're going to brute force it. Now, I know that the secret key for signing these JWT tokens is a 6-character password. It's actually a super secret password. The question is, can Hashcat find it? So let's just run this script and see what we get. We get the same type of warnings that my hardware isn't really suited for this. But there's a big difference between blowfish, bcrypt, which we use for the password encryption, and JWT hashing, and that is that the cost factor for JWT hashing should be a lot less because it happens at scale. right? So this is actually a cheaper algorithm to run with a lower cost factor. And this is also represented in the hashing rate for this script. So where earlier we got around, sorry, I believe about 60 hashes a second. Here we have 22,000 kilo hashes a second. This is also represented in the time estimated to crack this. We're only going to need approximately 15 minutes. Now, the only reason that this is 15 minutes is because I've told Hashcat I know the secret is only 6 characters. If this becomes 12 characters, 32 characters, etc., the time exponentially increases to try and crack this. So obviously, longer signing keys are very important. Use a long signing key to make your tokens a lot harder to crack. It doesn't make them uncrackable. None of these hashes are uncrackable, but it does make it a lot less rewarding for a hacker to go and do this because they have to spend the money and the time to go and do this. So let's move back to our web application and see what else we can find. So we've obviously logged in and signed up as a user, and we've found a lot of valuable information. But let's just continue and see, what happens if we say we signed up as attacker1 at gmail.com. And let's say we just put in the wrong password. The application comes back and tells me that this is the wrong password. Interesting. Let's also just, try this a few times, and what we see is that our application seems to allow me to do this indefinitely. Interesting. So we haven't signed up yet as attacker2, so I'm assuming that this doesn't exist. Let's see. Wrong email address. This is very interesting. All right, so just by using the application, I can see that the application behaves in a certain way and it's telling me too much information. I'm also pretty sure if I go and look at this, for example, we see, wrong password, and it's giving me a response that says wrong password, unauthorized. So the API itself is returning the same information. So I'm guessing that for wrong email address, it does the same thing as well. Yep, wrong email address. There we have it. So this is interesting. Best practices recommendation is that you just say, invalid email address and password configuration or combination or something. You don't want to give the attacker a clue about what it is that is wrong about this combination. Because if you give them the opportunity to identify that the email address is good but the password isn't, you're opening this email address, this user account, up to a range of potential hacks and threats again. Okay, so we've learned a few things here. First, we've learned that we apparently can keep on trying as much as we want, which gives us the possibility to start to script things very easily. The second thing is that we've seen these very verbose error messages that allow us to identify if an email address actually has an account in the system, yes or no. Now, with previous leaks, a lot of email addresses have already been leaked. So there's a wealth of information available to attackers on the dark web and elsewhere, where, if your email address was ever compromised in the attack on Peloton or LinkedIn or Twitter or whatever, in all of those past years, then there's a very high likelihood that your email address is in one of those libraries that you can find on the internet. If you're curious to see if your email address is actually part of one of those libraries, there's a good website that I can recommend, which is called Have I Been Pwned, which combines all of the information from all of those hacked websites. In this case, it has information of almost 670 websites. You just type in your email address, hit the pwn button, and it's going to tell you if your email address was in one of those leaks. And if so, it's going to tell you in which leak specifically. So have I been pwned? Very interesting. But at this point, what we're really interested in is that we know that these lists of leaked email addresses exist. So with what we know here about the fact that our API allows us to try and with each attempt is going to tell us very verbosely, is this a known email address, yes or no? We're going to try and identify other users that have accounts in the Deliver application. So let's go back and let's have a look at one of our resources that we have here. So I'll show you a list of leaked email addresses. These are obviously fake. I've randomly generated them, but for the sake of the example, let's imagine that these are email addresses that come from one of those leaks on the internet. So what I want to do now is I want to run a script that is going to try to log in with each of these email addresses. And I'm going to log in with one given password. Obviously, it's going to be the wrong password for all of these accounts. But by simply matching the responses and the error messages, my script will be able to understand if that account has, if that email address has an account in the Deliver app, yes or no. So I've written a little script called Deliver, and it has an option called Have I Been Pwned, and it's going to take that leaked file. It's going to run through, I believe there's 1,000 possibilities in here, and I know that I have 1,000 registered accounts in this demo application. So let's see out of this list how many of those 1,000 accounts can we identify. So it's running 100 batches of 10 emails against that backend API. The backend API is very fast in coming back. It doesn't rate limit me, it doesn't throttle me, it doesn't block me after any number of attempts. It just allows me to go through the entire list of 1,000 email addresses in our leaked.txt, and it found 6 email addresses. So these are email addresses that have been previously exposed in leaks on other websites that I've been able to identify as accounts in the Deliver application. So once I've been able to identify a number of accounts based on large libraries of leaked email addresses from previous breaches, I can actually use a similar approach to try and guess their password. There is a large library of passwords, unique passwords, that have been compromised in earlier leaks. The file is called rocku.txt. It's actually bundled into the default Linux distribution that is often used for penetration testing and hacking, which is called Kali Linux. And in Kali, rocku.txt is there. The 2019 version is in there. That has roughly 14 million in unique password combinations. The 2023 version of rocku.txt would have 8.4 billion password possibilities, but the sheer size of that file makes it unmanageable again. It doesn't really offer the necessarily cost versus reward in trying to combine all of those passwords possibilities with a single account. Also, because in recent years the use of password managers has become more popular, they generate passwords randomly and store them. Google has one in their Chrome browser. Apple have one in their Safari browser. You could use a password manager like 1Password. Since people have started to use those tools, the likelihood of being able to crack and guess a password has been reduced dramatically because you're actually left with no options but brute forcing. Unfortunately, or luckily in our scenario, a lot of people still use passwords that they've come up with themselves, right? A lot of passwords have one email address, a lot of users have one email address and one password that they'll use to create accounts at all of the applications they use. Now, if we're lucky and one of those passwords was part of a previous breach, a previous leak, then it'll be part of our rocku.txt file, and we can run those combinations against the identified accounts to see if we can get access. So let's see if one of those has been, one of those 6 here has been dumb enough to reuse their password across sites, even though it was leaked earlier. Now, there's 2 ways of doing this. One would be a traditional dictionary attack. We take the contents of rocku.txt. So let me just quickly show you what that looks like. It's just a list of passwords, and I've actually trimmed it down. This is only 1,000 combinations for the sake of time. The real version, as I mentioned, contains over 14 million unique password combinations. all of these passwords that are essentially, values that somebody at some point has come up with. So they're not randomly generated, they're actual passwords used at some point by actual users. So the first would be to use a standard dictionary attack where I run each of these values against each of the identified email addresses in the hope that they would have used one of those. Now, if I do that, then I'm running 1,000 in this case, password possibilities against a single identified user account. Now we know that in this case our API won't stop me from doing this. There's no rate limiting, there's no throttling, and I can try as many times as I want. So it'll work. But a common technique used in the real life, in the wild, is something called password spraying. Password spraying actually reverses the mechanics. So you've got a list of identified email addresses and you've got a list of possible passwords. What it's going to do is, instead of trying each password for each email address, it's going to try each email address for each password. So let me clarify. Instead of running 1,000 password combinations against one account and then moving to the next, it's going to take the first password possibility and run that against all the identified accounts, against all the user email addresses. This sometimes has the benefit that it enables you to work around any rate limiting and throttling restrictions that the server may have implemented. Sometimes they're advanced and they use things like the number of requests per IP address. Sometimes it's very basic, like the number of times you've tried a password for a given user email address, right? By applying this across long lists of user email addresses, you avoid the risk of hitting things like timeouts, too many attempts for a single email address, etc. You can't completely avoid it, but it may help you circumvent those. So my script will actually apply this password spraying technique. So it's going to run all of the combinations, or all of the credentials, in the RockU file, in this case just 1,000. I won't keep you here all day, against all of the email addresses that we found in our previous scenario. So if I just run this, it's going to run, like I say, 1,000 passwords. It's going to spray those across 6 email addresses. And we can see from the progress that it's making that it'll take about 2 minutes to complete this script. So I'll just let this run. I'll fast forward to when it's completed and we'll look at the output and see if we got lucky. Okay, we're nearly to the end, so I'm curious to see what we'll find. But needless to say, this is yet another case of a vulnerability called lack of resources and rate limiting. This is just allowing me to script anything I want, hit the endpoint, and see what I can get back. So here we see this took about 2 minutes to complete, and it found 2 credentials actually. So there's 2 people out of the 6 that have used known passwords from the rocku.txt file. So I'm seeing here that B. Chamkin is using cheerleader as their password, and C. Donald5 is using 098765 as a password. So these are now 2 user accounts that we've been able to compromise. By being able to compromise, I mean we've been able to actually access all of the profile information that is there for them in the application. We'll have a look at what the user profile is later on in a later scenario, so that's okay, I'll come back to that later. But just so you know, by simply exploiting the fact that there is no rate limiting and that there are error messages on the login method that are too verbose, I've been able to run large libraries of leaked email addresses against the login function to identify which email addresses actually have registered accounts. And then for those registered accounts, I've been able to use password spraying with a large dictionary of passwords from previous leaks to try and access some of these accounts. And I found 2 that I've actually been able to breach. So obviously this is a massive impact in terms of those 2 users. But the goal as an attacker is to be able to demonstrate impact across the whole user base. At least in this demo scenario it is. So, happy we've been able to breach these 2, but really we want to be able to access a lot more accounts. So we'll continue our research. and our reconnaissance. Okay, so let's continue our reconnaissance and see what else we can find. So we've already signed up for an account. We've tried to log in with the wrong password, the wrong email address, tried all of those scenarios. So let's see how the password reset flow works. So I'll use my account with which I signed up earlier, attacker1@gmail.com. Reset password. Oh, okay, I have to type it in again. Reset password. Okay, so we see we get a warning or an information message that says a 4-digit one-time password has been sent to our email address. This is a very common way of managing a password reset flow. The idea is that you need 2 factors to be able to reset the password, something you know and something you have. In this case, you need to know what the one-time password is, and the only way you'll be able to know what the password is if you have access to your own email box. So in theory, nobody else has access to your email inbox, which means you're the only one who would be able to know this. So let me just go to my email inbox and see what I got. Okay, so I got an email and it had this link in it, which I just copied and pasted. So I'll just go and visit that, see what happens. Okay, so the application redirects me to a password reset form. It pre-fills the email address and the one-time password, and I can choose a new one. Okay, let's choose a new one. But instead of resetting the password, let's just see what happens if I put in a wrong one-time password. Invalid one-time password. Okay. Interesting. I guess it really shouldn't be telling us that, but it is. So we know that we get a invalid one-time password back. If I put the right one in, okay, it allows me to reset and then automatically logs me in as attacker1. So let's have a look at the traffic that was generated here in man-in-the-middle proxy. So we see post to the auth reset endpoint. The payload was just the email address. So in theory, for any user that we've been able to identify, we can just request a password reset. That doesn't really help us yet, but we know we can request a password reset. And then there is a put operation. This was my first attempt with the wrong one-time password, so the wrong 4-digit code, which gives me a 401 unauthorized back. Okay. And then I've done another put with the right one-time password, and that just gives me a 200 OK back. Okay, so this is interesting. What we've learned here is that for any email address that we've identified, we can request a password reset. The password reset will trigger an email to the user's inbox to which we don't have access with a 4-digit code. What we've also learned is that when we get the wrong 4-digit code, we get a 401 back, unauthorized. If we put the right 4-digit code in, we get a 200 back. We already have established that this application doesn't use rate limiting. So what I can do is request the password reset for any user and then brute force the password reset for that user. So for the list of email addresses that I've identified, for each of those, I can go in, request the password reset, and then brute force all combinations. In this case, 4 digits gives me roughly 10,000 combinations. Brute force that 10,000 combinations to reset the password. So for all of the user accounts I've already identified, in theory, I can reset the password to something that I choose. Let's go ahead and try this. Okay, so let's go back to those user accounts that we've been able to identify earlier, but that we don't have the password for yet. So cat, demos, attack3, the email addresses we found. We already have the passwords for P, Chamkin, and C, Donald. So let's take L post L1. Let's just go in, I'll log out, reset or request the password reset for this user. this user won't actually ever notice anything except for that reset link in their email address, right? So right now we need to move ahead and just see what we can do. We've requested the password reset. We obviously don't know the four-digit code, sorry, because we're not receiving the email address ourselves. But again, I've written a little script. Reset password, which needs an email address as an argument. So I'll just put this in. This script will go and run. And what it does is it'll try all 10,000 combinations for that one-time password for this user. So there it goes. It's running operations against the auth reset endpoint, trying to get a 200 OK instead of a 401 unauthorized. So I'll just let this run. Again, I'll fast forward when it's nearing completion. Okay, and it didn't actually need to run through all of the combinations. After about 72 seconds, it was able to reset the password for this user account, which has now been set to "you have been pwned." So I can go take the email address, log in using the password that my script has set for it. And bingo, we're in. So now we're logged in as Leanne Postel. We've compromised her account by the reset password flow. So what we've seen here is a brute force attack on the reset password endpoint, right? If there were rate limiting, it would be a lot harder for us to do this. If this would have been combined with, for example, a time limit on the amount of time that you could use to use that one-time password, it would have been a lot harder for me to access this account or compromise it. So by adding additional layers of protection in the form of rate limiting, expiration times, etc., this would become a lot harder to virtually impossible. But because this application doesn't have rate limiting, we've actually been able to break its user authentication. So we've been able to now access all of the user accounts that we've previously been able to identify based on email information that come from other leaks. So out of the 1,000 users that the Deliver application has, we've been able to identify 6. We've been able to access 2 because their passwords were part of a dictionary from previous leaks. And we are able to access the 4 other ones because we can reset their password by brute forcing the reset password flow. So while this is all interesting, I've only been able to compromise 6 of 1,000 accounts yet. I'm not happy yet. I want all 1,000. So let's do some more reconnaissance. So let's explore a complete user profile in just a little bit more detail. So we know about the shop pages and everything else, but let's have a look at, a user profile, what it looks like when they're logged in. So we see the user profile obviously has, all of their profile information. So I can see the credit card information here. It's in clear text. It hasn't been anonymized in any way. There's also an order history page. So this user has actually placed 5 orders in the past, and for each order, we can see the details. Okay. Meanwhile, while I'm browsing all of this, man-in-the-middle proxy keeps collecting all of those API calls. So let's just have a quick look at what it's been doing here in the backend. So we've logged in, we've accessed the user profile page. I'm guessing this is /user, the endpoint for the user profile page. The request is just a get, and the response is the full profile. Okay. We see there's no parameters used in the query itself. All that's used is the bearer token, so the JWT token. So we have to assume that the JWT token is what the application is filtering the user information by to present here in this form. But we'll try some different options later and see if there's anything we can do to work around that limitation. And then the order endpoint, we see here get order. Same, it's just a get with the bearer token, and the response contains a list of all the orders. Okay. So all the order information, what was ordered, etc. Order lines. This is interesting. So we see that for the order, it actually has a link to the user object. So the user ID and the email address for the user are part of that order history information. We don't see that here in the screen. It doesn't actually surface anywhere, but obviously it makes sense that the query needs to limit somewhere based on the current user that is logged in, and it seems that that link is available in the JSON information that is being sent back. All right, so in this case, the user interface itself doesn't allow us to do much. But let's go to Postman and see if we can mess around with this a little bit and see what we get. So I'm going to log in as an existing user, just so I have the token. Okay, and now I want to try a couple of different options. So first, let's get me my own user profile. I'm logged in. Yep, this API endpoint works, /user, and it gets me back all my user details. Okay, so what happens if I start to play around with this REST endpoint? See if I can introduce path parameters, query parameters, etc. Maybe I'll just I'll sign up as a new user. All right, log in as the new user. So I have a new token now. And when I get my own user profile, I see I get my new user profile, which is very limited. But let's try to get that known user now. So we have Odile. Let's try with a path parameter. So I'm logged in as Madeline, but I'm trying to access Odile's user profile by providing the email address as a path parameter. And it doesn't like that. 404 not found. Okay. So let's try as a query parameter. We've seen this before in the reset password flow. Email as a query parameter. So let's just give it a go. Unfortunately, it just seems to ignore the email parameter because it's giving me my own profile information back. And then finally, we did get the user ID. We don't really have it anywhere else, but we did find it in the token when we logged in as that user. So let's just see if it works. But that also gives us a not found. So it seems that for the user profile, we really can't work our way around the automatic filtering that is done based on the contents of the JWT bearers token. All right, fair enough. So let's see, this order history. I want to log in as Odile again because I want to have an order history to check out. So let's see. This one has an order history. We've seen this user identification before in man-in-the-middle proxy. That's good. We see the order information that was placed. Okay, but we still just have an email address. All right, let's see. We've got order IDs. Yeah, we've got a number here, 2234. So there's nothing in the user interface that uses this order number, but it would be very common in RESTful APIs to actually have a path parameter that accepts that and returns that single order's information. So let's just give it a go. All right, we see that this works. We get 2234, and it gives us back that one order. Yeah, just one order with all of its details for my user. Right, so now what I want to try is I've got this little script here. As the result of my get order, I've set a collection variable to be next order 2235. So I'll just try the next order, 2235, which I know is not an order of this user because 2234, and then the next order they place is 2248. So 2235 is not an order of Odile. So this is going to try and get that next order, and then In the end, it'll increment that order number every time, just see what happens, see what it does. So I'm going to try and get 2235, and I get 2235 back. And I see that this is for P. Chamkin, another user we've compromised earlier, but this is not the user that we're currently logged in with. So it's giving me order information for another user just by increasing the order number here. Interesting. So 2236, yeah. This is a user we haven't seen before, so this is a new email address. This is a new email address too. And it seems we can just keep on going and enumerate the numbers and access order information that we are authenticated, we are logged in as Odile. So to the backend system, we are an authenticated user, but it seems there is no authorization logic implemented on the backend that restricts me from seeing other users' orders. This is what the OWASP API top 10 refers to as a broken object level authorization, or a BOLA. A BOLA essentially means that as a user, you have access to another user's information. So this is an example of a BOLA. Now this is interesting because what we can do here is simply by enumerating all the order numbers, we can extract all the email addresses. And we already know that if we have an email address, it's just a matter of seconds before we've been able to reset their password and access their account. So what I want to do in this next attack is actually script the enumeration of the orders, try to extract as much order information as I can out of the system, and for each of those orders, extract the email addresses and compile a list of unique email addresses. Essentially, I want to find all 1,000 users in the Liver application. So let's go and try that script. So let's clear the screen here. So I'll use my little script, which is deliver orders. I'll just use, so let me just show you the help, orders. So orders needs a token file, so it needs a valid token, and then it needs a file as output. So deliver orders, use the token I got earlier, and then write it to a new file called emails.txt. So what this script is going to do is going to run across the order endpoint, is going to query all of the orders. Lower value 1, I'll accept the default. Upper value 5,000, I'll accept the default. I don't know how many orders are in the system, so maybe I'll run again later to get more. But let's try the first 5,000 orders and see what happens. See how many emails we can get out of that script. So let's just run this. You see it's pretty fast. It's moving over all the orders, getting me all the information. All right. And it tells me that in 9.6 seconds, it has extracted 1,000 email addresses from 3,009 orders. So the system doesn't actually have 5,000 orders. There's only 3,009. And it's been able to pull all 1,000 email addresses out using the BOLA. So if I now do demos attack 5 emails.txt, I have all 5,000 email addresses, all 1,000 email addresses for all 1,000 user accounts. This means that I've now successfully been able to compromise each and every account in the Deliver application, because what we've seen in previous attacks is I can go and run a dictionary attack, or even easier, just simply reset all of their password to the password of my choice. And then I'm able to access all of their accounts, get all of their information via the user API, and leak all of that information in theory if I were an attacker. Obviously, that's not the point. In this case, we are white hat or penetration tester. Our point is to be able to prove that we have access to this type of information and then be able to report it back to the owner of the application so they can plug the leaks. What is a very important lesson in this demonstration that I want you to take away with you is that the real risk isn't necessarily in a single vulnerability, but the real risk is actually in the combination of vulnerabilities. The fact that I can brute force the password reset flow, the fact that I can enumerate and brute force order information and extract user accounts from that combination enables me to access all user accounts in the system and compromise them. So it's not a single vulnerability, but it's actually a combination of things that happens. And attackers will actually always try different angles, explore that attack surface, map out what they can find, and they'll be creative in trying to do things that aren't necessarily part of a web application, that aren't part of the user interface, but that are common patterns with APIs, and they'll try to abuse those to their benefit. Now, I want to show one more thing before we go, and that is that there's actually another way that we would be able to breach this application. Something that attackers are also always looking for is not just to get access to user information, but is also to identify ways where they can elevate permissions for their own account. So let's see if I can create an account that has elevated permissions, right? A lot of applications use development frameworks in the backend that make it easy for the developer to speed up development. We've already seen one side effect of that. The default example of creating a JWT signature that you'll find on Google often leads to the fact that there's too much information in JWT tokens. It's easy to leak information if you don't think about all the additional steps that you should take for sanitization of that JWT payload, etc. But in this case, I want to make my own account an admin account. Now, I haven't seen any evidence that there is the possibility of logging in as an administrator, and I don't know what that would actually do as an attacker, but I can demonstrate it to you because I've obviously created this application. If I log in as administrator, I have this extra admin option, and this extra admin option gives me access to all the users in the system. So it gives me a list of all the users that have been registered, and I can see all of their information, all of their details, and we see there's 10 per page, so there's a little over 1,000 now because we've got a few extra test users in. So my point is, in this scenario, to try and see if, as an attacker, I can get administration rights. And we'll try a couple of things. Obviously, the normal login form, we've tried that before, or sign up form. We've tried to log in as attacker1@gmail.com, and it doesn't give me any elevated permissions. So let's see if we can create some other variations of accounts by using the API. So I'm going to try and sign up as administrator. We've already seen in man-in-the-middle project proxy that when we log in, or when we sign up, we pass in an email address, a password, optionally a first name and a last name, or any of the other profile fields. So I want to see if I can just add more fields to that profile, which would be interpreted by the application as giving me elevated permissions. A very common role management type of system or logic in applications would be to give a user profile a property, like, are you an admin? Yes or no? What role do you have in the application? So we're going to try a couple of these and see what happens. So I'm going to try and register admin try1 with password 123 hashtag as the password. And I'm going to set the property admin to true. So let's first see what happens. Okay, we see we get a 200 back. So it's actually accepted this registration. So let me just copy the email address. Let's log in. Admin try1 123 hash. Did I type that correctly? Yes, I did. Log in, and it actually does allow me to log in, but I don't have any elevated permissions. Right? We know to expect this admin menu here, but there is nothing here that looks any different from what an attacker would have seen when they registered without that property. So this didn't work. But let's try another way. Let's set the role to be admin. Right? So I'm just adding a property to the object. Say role admin. See what happens. All right, so again, I'm getting a 200. So pure payload wise, this has been accepted. Now let's go and see. This was admin try 2 with the same password. Typo. Let's just double check. Yep, log in. All right, now let's me log in again. And now we see we did get the admin field. So even though the user interface in the web app itself doesn't allow me to put that field in, doesn't allow me to say I have the role admin, when I use the API directly, I can. It hasn't been documented anywhere, but just trial and error, some reverse engineering, I'm able to sign up as an administrator. And once I'm signed up as an administrator, I actually have a valid administration token that lets me access more endpoints. Because we can see those here. We have admin/user, which I can access and just enumerate all of the pages of user information and extract that information from there. So if we just have a look at this, we see the request is simple. We've got our bearer token, which now has the admin role included in it. Page 1, size 10, and I get 10 user objects back with all of their information. So at this point, what I've done is I've exploited a vulnerability that is called mass assignment. Mass assignment may not be the most intuitive name, but essentially what it means is that a lot of development frameworks, whether it's in Node.js with JSON, in this case the raw JSON just gets stored into the MongoDB, so there's no sanitization or validation anywhere in between. But it happens the same with other stacks of technology. For example, Spring Framework will also allow you to automatically bind JSON documents to Java beans, right? So as long as you define the right Java bean structure and that JSON property is accepted by that Java bean structure, it automatically gets serialized and deserialized and stored in the database. So mass assignment essentially means trying to exploit known productivity features of backend frameworks to try and give yourself, in this case, elevated permissions, but it could be anything, right? And ultimately, the goal is to be able to insert data that gets accepted by the system as if it is valid data, but it really shouldn't have. And in this case, I'm using it to give myself admin permissions. And by giving myself admin permissions, I have compromised the entire set of user accounts in the Deliver application. Okay, that was quite the lengthy demonstration, but there were a couple of things that I wanted to show you. And now for wrapping up the session, I just want to call out a couple of things and bring them to your attention. So first thing that I've wanted to call out is I've used one of the public data breach calculators. There's a variety of different options out on the internet that will help you estimate the cost associated with a data breach. And I've used one of those calculators to estimate the costs for the data breach that we've just demonstrated. And these breach calculators, they essentially take a couple of parameters. They're not too complicated. Usually it involves questions like, does it only contain internal information to your company, or does it also contain customer records? How many records were involved in the breach, and what type of data is stored in those records? Is it personal information, payment information? Does it include health information? Depending on those categories of data that may have been included in the breach, there will be different types of fines and assessments and other things that need to happen. So the cost may increase or decrease based on those parameters. Now, for this breach, it has customer records in it. There's 1,000, and the records include both personal and payment information, which leads to a cost estimation of over $500,000 for this data breach, a cost of $562 per record, actually. Now, that estimation includes things like the forensics in investigating the breach and trying to fix the leaks and plug the holes. It includes crisis management within the organization, but also externally in terms of public relations and other things. And it includes things like fines imposed by regulatory bodies or payment card industry, compliance, etc. Now, what if this breach were a little bit bigger? Let's say that Deliver had 1 million customers and all of their records were breached. Then just by changing that parameter, you see that the total cost estimation for this breach increases to $12 million. The good news is that the average cost per record decreases to just below $12, but obviously the overall cost of the breach is a lot higher than it previously was. Also, because of the sheer number of records involved, the number of customers involved in the breach, there's an additional type of cost that is introduced into the mix, which is class action settlements. If there's large groups of customers involved, class action becomes a very real risk, and you'll have to take care of the settlements, but also the defense in those cases. So this demonstration has showed you what can happen and what the risks are associated with it, but what can you do to protect yourself from these types of vulnerabilities? Well, to protect yourself, there's really two types of challenges that you need to address. The first one is that APIs have become really, really common, right? Every digital project within your organization will be using one or more APIs, and you'll have multiple projects going on at the same time. So where in the past an API was something of an exception and a single door into your enterprise, today there's a sprawl of APIs, a lot of different teams building APIs, using APIs, and publishing APIs, and they're not necessarily all centrally governed. In fact, one of the strategic planning assumptions by Gartner is that by 2025, less than 50% of an enterprise's APIs will be managed. And this has to do with the sheer volume of APIs that is being produced and published. Now, another challenge, which is slightly related, is that the need for speed leads to more teams that use disparate tools and technologies. In fact, multiple digital projects will be going on at the same time, especially within larger enterprises. Those projects will be creating and consuming APIs, and for the sake of speed and productivity, not all of those teams will be using the same centrally dictated or centrally prescribed technologies and frameworks. Right? The days where the corporate standard was .NET or the corporate standard was Java with Spring Framework are behind us. Today there is a sprawl of technologies and a sprawl of tools that are used across all of these different projects, and you need to deal with that reality. You can't enforce a single stack to be used anymore. Now, those are two challenges, but I also want to highlight the types of risks and the types of vulnerabilities that exist. So knowing that there are a lot of APIs that are being created and being consumed within the organization, that not necessarily all of them are being governed and managed, and that a lot of them are being created with different technologies and development languages and development frameworks. It's really important to understand the types of risks and how they could be categorized. And the OWASP organization has done a very good job of classifying or categorizing those risks. And they actually have defined an API top 10. So these are the 10 most important types of vulnerabilities that exist within APIs and that they've identified. Now, just within the scope of this demonstration, we've seen 6 of the 10 OWASP API top 10 vulnerabilities. We've dealt with broken user authentication, where tokens have been compromised and potentially cracked. We've seen excessive data exposure with too much information being exposed on both the JWT tokens and the customer profiles themselves. We've seen a lack of resources and rate limiting, which has enabled us to brute force and dictionary attack some of the endpoints. We've seen security misconfigurations with the 2 verbose error messages. And then obviously the broken object level authorization and mass assignment vulnerabilities, which have both led to us gaining complete access to the entire customer base of the Deliver application. So with these two challenges to address, that sprawl of API and that large disparate set of tools and technologies within the organization, and these known risks, what can you do to protect yourself? Well, to me, API security really is built on top of 3 pillars. And the purpose of these 3 pillars is to enable teams with powerful guardrails. The days that we can restrict the types of technologies being used within an enterprise are behind us. For the sake of productivity, for the sake of innovation, for the sake of time to market, decisions are being made in a decentralized way. So to ensure API security, the crux really is to give powerful guardrails to the teams. And giving them powerful guardrails means that they don't necessarily need to know all the details about how to protect themselves from these types of vulnerabilities, but that these guardrails help them protect themselves in an automated way. And these three pillars to me are built around full lifecycle API management and something that I like to refer to as shift left and shield right. I'll start with full lifecycle API management. With an API management solution, and particularly the combination of something like a catalog, which collects the complete set of APIs that you have within your organization and that publishes the documentation for them, that prescribes how people can get access and have actually a workflow to provide people access, in combination with an API gateway that provides access control and protection and monitoring, is the centerpiece of an API security strategy. API management provides protection in ways that you can centralize, so people don't actually need to understand, for example, all the intricate details of JWT tokens, or they don't need to understand how to effectively do rate limiting for their APIs, because these are protection policies that you can implement on the API gateway in a centralized way, in a standardized way, so that you can assure that all of the APIs that are published via your API management solution have an equal level of protection. So API management is the centerpiece of API security for me. But it is very important to complement that with what I've called shift left and shield right. And some people might refer to this as testing and monitoring. That's okay. I just think that shift left and shield right covers the load better. The idea behind shift left is that you push as much of the validation, testing, and confirmation of best practices as early into the development lifecycle as you can. So this means that you give development teams the tools to understand what they're doing and to understand if what they've been doing is conformant to the security standards that you want to enforce. And there's a couple of recommendations I want to make here. The first is make sure that you practice API first design. One of the key things with APIs is that you need to understand what an API is going to do for you. So what are the functionalities that this API provides to the API consumer? But it's equally important to understand what the API shouldn't be doing. And an API specification or an API contract does exactly that. It specifies what the API does, and by doing so, it also specifies what it shouldn't be doing. Anything that isn't in the contract shouldn't be possible. That contract is a medium which can be shared throughout the entire API lifecycle that enables other tools to provide automated validation and automated testing against those APIs. So yes, the team needs to understand how to design an API specification, but once that exists and once it's plugged into the CI/CD pipeline, you can apply things like static analysis of the contract and code. You can do things like conformance scanning. Does the code only allow what the contract specifies? And automated penetration testing. It's very important that these tools get integrated into your DevOps processes, get integrated into your CI/CD pipeline so that you can standardize them across the lifecycle for all projects, no matter what technologies are being used, no matter what frameworks are being used, and no matter what the maturity level of the team that is developing those APIs. So shift left is a second important pillar. And then finally, the third pillar is shield right, which is where we're focusing on monitoring security aspects of APIs. This can be attack surface mapping, for example, identifying, all of the APIs that you have published, all are of them under governance. Do we have them in our catalog? Are they protected by the gateway? Or are there some rogue APIs deployed that we need to take under management? Are those APIs all secured? Do they implement the best practices, which is posture management? And then behavior analysis is where we could apply techniques like machine learning, for example, to understand Are APIs being used in the way that they were intended to be used? Are APIs being used differently by some consumers in unexpected ways? For example, suddenly a user might start to scrape API endpoints and collect information. Is that normal behavior? Yes or no? If it isn't, we may have detected a threat that we want to respond to. So threat detection can provide feedback into the API gateway solution to go and block that specific consumer or invalidate that specific token. So really what we're dealing with here is three pillars that play in synchrony with each other, in symphony with each other. The centerpiece is the API management solution with the gateway. That has the possibility to standardize your security and enforce it across all APIs, no matter how they've been built and who manages them. But you want to push validation as early in the lifecycle as you can with shift-left solutions. And you want to validate, monitor what is in production with shield-right solutions. So this concludes my demonstration and session for today. Thank you very much for the time you've spent with me. We're Software AG. We're a leader in API management with our Web Methods API management solution. I encourage you to go to the website and visit these resources, and they will help you to learn more about our solution. Thank you very much for your time today, and until we meet again.